All right, let's go ahead and quickly go over how to find variance from a frequency table. Just like we talked about with the finding the mean from the frequency table, if you don't have the original data and all you have as a frequency table, this would be the best that you could get for an estimation of the variance. And the more symmetric the data, the more accurate it's going to be. We're going to use our per snatcher data again. I filled in the frequency table for what we'd already found. Here's the computations over here. You can look back to the videos on how to find the mean for the frequencies if you want more explanation there. So we're just going to pick up by finding the x squareds. Well, our x's are our midpoints, so we're just going to square those. So we're going to be squaring 20 for the first one here. So we're going to get 20 squared, which is 400. And then we're going to square 29 and get the second one, 38 to get the fourth one, or third one, and 47 to get the third one. So I'm going to pause it, and when you next see this, it's going to come back with all these values magically filled in. All right, there they are, magically filled in. Now the next thing we want to do is we want to multiply these squared x's by our frequencies. So our next one is to be multiplying this times 3. And that's going to give us the 1200. And then the next one, we're going to multiply 841 by 4 and 1444 by 2 and 2209 by 1. So this is 2209. I can do that one, I think, in my head. And this is 2 and then 3/8, 2,888. And finally, this one would be, let's see, 4 times 1, 4 times 4, carry the 1, so 3364. And then finally, what we need to do is we need to add the sum of the, we need to sum the f times x squared, so we can get the sum of the f times x squareds. And I'm going to do that, and so when you next see this, it's magically going to appear down here. Right, so here's our sum of our f times x squared, it's 9,661. Remember that this was the sum of the f times x is 339. So now we're just going to plug into this formula. So right down here, I'm going to put in n, which remember that was 10. You can find that by adding up the frequencies. And then I'm going to put in the value for the sum of the f times x squared, which is 9,661. And then I'm going to put in minus, and then I'm going to do my sum of my f times x quantity squareds. So that's sum of the f times x's, that's 339. And then once I put that value in, I square it, and then I'm going to divide by 10 times 9. And finally, I'm going to do all of these values, and then I'm going to subtract this minus this and get that value, and then I'll divide by 90. So the next time you see this again, you're going to put those in. So you might want to pause it, try to do it on your own, and then put those values in for yourself. All right, so as I did this, I discovered an error. I discovered that 339, when I squared it, was bigger than 96,610. And that's a big problem because your variance can't be negative. And so I knew that something was wrong. And so my suspicions were that I had some frequency wrong or I had a midpoint wrong. And so I went back and I took a look, and indeed the issue was with 29 times 4. And so that was, let me see, 29 times 4. I think I wrote it in here correctly. That's 116, not 156. Don't know where I got that problem. So when we'd reported our x bars back there too, that one would be incorrect now because x bar should really be 29.9 divided by 10, which makes it a lot better than what we had said it was. 29.9 is a lot better estimate than we'd said 33.9, right? So this is a lot closer, and that shows us more of what we think is that that this data isn't maybe as skewed as we thought it was. So now this, I have to square 299 because I had, spent some time working on this here. So now I have 96610 and 894 4, 1. One of the points I'd like to make there is, you know, we're all human. I'm just as infallible as you guys are, so I don't make, I don't have error-free times either. But I am careful when I go through and I make computations that I don't ignore things that are out of the ordinary. So now 96,610 minus that answer I got, 89,401, is going to give me 7,209, and that 7,209 then I'm going to divide by 90, and divided by 90 is going to give me 80.1. And remember that these are 80.1 years, and 81.1 years may not be, or years squared may not be the best thing to give because I don't know what a squared year is. So I might want to take the standard deviation of that, or find the standard deviation, which is the square root of s squared, right, the variance, and that I'm going to just report as 8.9 for us. And remember that we got a variance, or a standard deviation of 10.9, I think, for our information. So this is an approximate value. It's not a bad approximation, but it's definitely not going to be the same as that computed from the original exact data. So that leads us on to our next discussion, which is something called the range rule of thumb. Now, the range rule of thumb is dependent upon something called the empirical rule. We discussed in class, at least, a little bit about the empirical rule. And the empirical rule, I can't remember exactly if I talked about it in the videos prior to this or not, but remember the empirical rule says that we have 68% of all data between plus 1 and minus 1 standard deviations of the mean. And if we're talking about the sample, then it's x bar and s. If we're talking about population, mu and sigma here. And 95% of all data within 2 standard deviations of the mean. And then within 3 standard deviations of the mean, we have 99.7% of all data. And this is plus or minus 3 standard deviations. And then the other thing that we note is that this is the values that are usual. Triola is big on this idea of usual. And that means that we have our minimum usually at x bar minus 2 standard deviations, and the maximum at x bar plus 2 standard deviations. And if we use this as the minimum and the maximum, almost all data is within that. So that's 4 standard deviations out that we're looking at most of the data. And that is where our range rule of thumb comes from. Our range rule of thumb says that we could approximate the standard deviation if we didn't have it. Now, if we have it, this wouldn't apply, okay? In there, range rule of thumb. We have our range of data divided by the 4, so plus 2 and minus 2, right? That's where we get 4. That this would be approximation of our range or our standard deviation, and that's what it is. So if we look at our bike racing data and we look at the range for that data, so our bike racing data back here, let me just scroll this way, it'd probably be the easiest. Our bike racing data, we had a smallest point of 21 and a largest point of 37. So we have 37 and we have 21. And if we divide that by 4, what do we get for the variation? So we have 6 and we have 16 and divided by 4. And that is going to be equal to 4. So this says that S is approximately equal to 4 for that bike racing data, so 4 minutes. And let's go back and see what we actually got when we calculated that. I don't remember. bike racing times. Let's see, here was the purse snatchers, that was the variation for that. There's the bike racing times here, and we used both defining and computational, and we got a 31.9 minutes for the variance, so 39.1, let's see, the square root of 31.928571 is equal to 5.6, so S is approximately equal to 5.6505 there, or approximately 5.7 minutes. So what we're saying is that just as a kind of an overall approximation, to use the range rule of thumb, what we would end up for the bike racing data is about 4 minutes. Not a great approximation, right? Because we see that the actual is 5.7. That's a minute, 1.7 minutes off. So not a perfect idea, but it gives you a general idea. Now, one of the things that we didn't look at all for the bike racing data is, what was the distribution of the data? Was it skewed? Was it symmetric? What did it look like? So it might also be helpful here to take a look at something like the purse snatcher data. So what would S be approximately for the purse snatcher data? So the purse snatcher data, we had a 50-year-old, and then minus the youngin, the 16-year-old, and then divided by 4. What does this give us? And so here we see that 50 minus 16, that gives us 34, and that divided by 4 is going to give us 8 and 2 left over, so 8.5, so 8.5. And that would be for the purse snatcher data. And we see that it's still a little bit off because we got 9 point something for the purse snatcher data. So yeah, we're not getting exact. Well, what it really depends upon is this data symmetric or not? If it's symmetric, then it's going to give us a better approximation because it's better going to follow the empirical rule. And if it's not symmetric, then we're not going to get the best information possible. So the empirical rule is a key here for knowing that this is symmetric data. Now, if we don't have symmetric data, one of the things that we might use would be something called Chebyshev's theorem. And Chebyshev's theorem says, okay, well, if we don't have that symmetry, then we can approximate the value of the percentages here in a little different way. And we don't have a rule of thumb that goes along with Chebyshev's, but we can certainly talk about percentages. So if I have skewed data, and I want to talk about percentage of data within a certain range of the mean, then I can talk about this. So Chebyshev's, and sometimes you'll see Chebyshev's spelled differently because Chebyshev was a Russian mathematician, and it gets translated differently sometimes. So Chebyshev's theorem says if I have 1 minus 1 over k squared, and this whole thing is, this squared, sorry, we'll put this down inside. It doesn't technically matter, but we'll put it inside. Percent of the data and this is within k standard deviations of the mean. And when we're talking about these skewed data sets, k has to be greater than 1 or we end up with 0. So that's where I'm going to end for right now, and we'll apply that in the next video.